Welcome to the session 1A on physical computing. So before starting off the session, I would like to ask all the authors to rename themselves using the paper ID and their name.
Excuse me, isn't this supposed to be 2B?
Pardon for the mistake. So welcome to this session 2B physical computing. Now let me introduce you to the session chair, Professor Roshan Darshanayapa. So he is currently working as a professor in statistics and computer science attached to Department of Statistics and Computer Science, Faculty of Science, University of Peradeniya. He obtained his bachelor's degree in statistics special with a second upper class honors from University of Sri Jayawardhanapura in 2001 and his master's degree in computer science from University of Colombo School of Computing in 2005. Then he obtained his Doctor of Engineering in Information Engineering from Hiroshima University, Japan in 2008. His main research interests are medical image processing, computer vision, data science, machine learning, and computer graphics. So, Professor Yapa, I invite you to lead the session.
Thank you, Hiransa. Good afternoon, everyone, all the authors and the participants for the session 2B, physical computing. So in this session, the first paper to be presented in this session is, the title is Towards Developing a Simple Lumped Parameter-Based State Estimator for Neonates. The author is Ms. Tisara Pathirana, has graduated from the Open University of Sri Lanka and currently he is working as a lecturer probationary at the University of Kelaniya. So you'll be having 50 minutes for the presentation, all the main presentations, and 5 minutes for the question and answering. Over to you, Mr. Tisara Pathirana.
Hello everyone. This presentation under the research topic toward developing a simple lump parameter based state estimate for Neonate. I'm APTD Pathirana. Is the content of this presentation. We have to discuss about Neonate actuator under the introduction, mathematical model and lump parameters. And we have to discuss our methodology in point of view of experimental setups, parametric estimation, finite element analysis, results and conclusion. Before we getting into our main topic of this research, we have to discuss about soft robotics. You can see it's a robot with having rigid link kinematics and other dynamics. And also here is a gripper with having soft behavior. Neonate type actuator can be used to develop these kind of soft grippers. You can see a virtual reality based gesture control systems in soft robotics research laboratory of the Open University of Sri Lanka. We already use Neonate type actuator to develop this soft gripper. So when we discuss about a parametric estimation of Neonate type actuator, we have to know about the bending behavior of Neonate actuator. Here is the Neonate actuator. There are two types of layers. in these kind of actuators, soft actuators. First one is active layer. It can be used to inflect a compressed air for bending. And the other layer can be defined as passive layer. It can be used as a strain limiting layer for the bending process in this Neonate actuator. And basically a molding type technique can be used to fabricate this Neonate actuator. You can see a molding and material mixing and other process under these steps. These steps is describe a fabrication process of Neonate actuators. So when we discuss about lump parameters of Neonate actuator, uh, any physical parameter with having independent variable and without a function of time can be defined as lump parameter. In mechanical point of view, mass, spring coefficients, damping coefficients are lump parameters. Also electrical, resistance, capacitance, inductance can be defined as lump parameters. In our research, the already estimated spring coefficient and damping coefficient of this Neonate actuator during its bending process. This kind of mathematical model can be used to describe a bending behavior of Neonate and the other lump parameter behavior. You can see this one. It's a bending process of Neonate actuator with having inflected air. First, we develop a hypothetical disk model to describe the bending behavior of this soft actuator. By considering these kind of hypothetical disk model, we govern this typical second order differential equation to describe moment of inertia, damping coefficients, and spring coefficient of this Neonate actuator. You can see here, it's a torque. This torque can be defined as an input of this differential equation. So we can replace this torque using force and other forced acting length. On the other hand, we can replace this force using applied pressure and other surface area. Then we can generate this equation to describe the bending behavior of Neonate actuator with a function of pressure. Now we can develop this second order differential equation as a state space representation to calculate a mathematical response of this dynamic system. In point of view of experimental setup, we already use Neonate actuator with having a flex sensors. And Arduino is used to execute a control algorithm according to our desired input. And solenoid valve and pressure sensors are the actuators and also feedback to control our bending process. And you can see a complete video demonstration here. And we can define a bending process of this Neonate actuator according to our desired input. Now, we already know about this kind of second order differential equation functions. When we do our parametric estimation process, as I said earlier, we have to estimate a B, also damping coefficient of these systems, and K, spin coefficients of these systems using parametric estimation model. This kind of mathematical model is provided for MATLAB to get a model response. And under the parametric estimation process, we already govern the actual response using these flex sensors. According to the actual output of the system, we have to overlap this mathematical response on this curve. You can see in figure 9 before estimation and figure 10 after estimation. You can see here this mathematical response and actual response is overlapped after the parametric estimation process. Those are the main technique in parametric estimation. In our case, we can control a k value with having a constant of b. Then we can see a special behavior of this curve to vertical movement. And when we control b having constant of k, then we can control horizontal movement of this mathematical model. After the changing and after the adjust these kind of values simultaneously using our parametric estimation algorithm, we can obtain this kind of fine-tuned actual response like mathematical response with having these kind of tolerance. You can see this simple demonstration for our parametric estimation process. And you can see this one. This is the parametric estimation process, our entire methodology. You can see the adjustment of K and B during these kind of parametric estimation algorithm, and we obtain the best K value and B value with representing a minimum response error using surface curve. That now we can see here is the overestimated response, but it's already record a best value using that kind of surface response analysis. Now you can see this surface response to obtain the best K and B value according to our parametric estimation algorithm. So we can define this kind of K and B value as a final value. When we discuss about finite element analysis of this soft actuator, we already use Abacus software by mentioning the actual fabrication material, Elastosil M4601 silicon rubber, with having these kind of physical parameters. And we already use Neo-Hookean strain energy potential defined by these kind of Neo-Hookean coefficients. And we investigate the bending behavior according to these kind of air inflection for this Neonate. You can see the parametric analysis results for our main finite element analysis systems for Neonate. When we discuss our result, we have to discuss our main progress. We already conduct 3 types of tests. In first test, we already use step input pressure, and we already govern the actual response using sensors and parametric estimation process. We obtain K and B value. Then we already calculate RMS error, root mean square error. After that, the estimated K step and B step already used to test sinusoidal input pressure. After that analysis, we already use another parametric estimation process with having sine input pressure. Then we already govern the actual response of these systems, And we already calculate root mean square error for these separate systems. This is the main 3 types of test to govern our results. And you can see those are our results of these systems. Now you can define those are the 5 main step response for 20, 30, 40, and 50. After that, you can see the sign response of this parametric estimation process under the earlier number of tree tests. After that, you can see this graph to describe the root mean square error according to each test. You can see under test 1 and test 2 and test 3 for this process. And we already govern a best root mean square error value under the test 1. In conclusion of this research, these kind of system approach 80% accuracy by mentioning this kind of parametric estimation process. And the average root mean square error between a result of a hypothetical disk model and experimental result is less than 4%. Finally, we can conclude that the hypothetical disk model is an accurate estimator for these kind of finger-like soft actuator. On the other hand, we can conclude these kind of hypothetical disk model. These kind of hypothetical disk model can be used as a accurate parametric estimation for these kind of Neonate actuator. And you can see the reference, and thank you very much for your attention.
Thank you, Tisara, for your valuable presentation. Now the session is open for questions. If the audience has any questions, you can ask from Mr. Tisara.
Thank you, Tisara, for the presentation. I think among the most papers I saw in ICTA, I think this is one of the hardest papers to understand for me, at least. Probably because of I think it's more towards mechanical engineering, I guess. There are more into like material and stuff like that. So okay, so if I understood correctly, so in this work you are trying to estimate like how much pressure we need to apply in order to make a certain amount of move on the software actuator. Is that correct?
I think, thank you, Asanka. And the main focusing area of this research to estimate parameters during the bending process of actuator. As I said, as you said earlier, for a pressure apply or something, when we describe a dynamic systems in these kind of gripping tasks, it's unable to measure those kind of parameters without any physical testing or something. We already focus to measure the specific parameters, spring coefficients and damping coefficients for a bending of this Neonate actuator for soft robotics application. We already estimate.
Yeah, so the lump parameter in this particular application is the what exactly is it? Is it the angle?
No, the lump parameters of this application is spring coefficients of bending Neonate and damping coefficients of bending Neonate actuator.
So that K and the other one, right?
K and P, yeah.
Yeah. Okay, okay. So I have two questions actually. Now I understand it. That I think. So what is the material you use for this particular soft actuator?
We use elastosil material, silicon rubber M4601. It's type of silicon rubber.
So with time, I don't know whether in the last phase of your evaluation, maybe this is what you evaluated. I don't know. So with time, will the characteristics of this material change? I mean, causing your model to be incorrect. I mean, eventually when you make it, use it for a particular application, and this soft material can, I don't know, wear and tear. Is it possible?
Yeah. Sure. That kind of that time is depend on the fabrication process of these materials, because if we use any large press or something, then we can mix. We can change the mixing ratios or something other things. So it's depend on the process. Generally, we spend about 15 minutes to cure the our materials or something.
Okay. My last question, sorry.
Sure. No problem.
So in your slide number 10 and 11, the graph you showed, what was that x? I mean, the variable was named as x, but it was in the y-axis. What exactly was that parameter?
Sure.
I guess it is the angle. I guess with.
So let me share my slide show.
I can share the slides if you want.
Sure.
Okay.
That was on slide number 10 and also in 11, and both had the same kind of graph. Yeah, these ones. Yeah.
This
so
one.
in y-axis, yeah. So what do we see here in this blue line? Is it the expected?
The blue line can be defined as a mathematical response of our real systems, and the orange line can be defined as an actual response of our Neonate. So that kind of actual response can be measured using a flex sensor on our experimental setup, and our main focus is we have to overlap our mathematical response on our actual response by changing a K and B. After that, we have to continue many number of 100 and 1,000 number of steps to describe these kind of parametric estimation, and then after the finalization of our estimation, then you can see figure 10. It's the best response to describe the actual behavior using our mathematical model. So you can see the x-axis is an angle and t is a time, execution time of our system.
Okay, thank you. Sorry for taking too much time.
No problem.
Yeah,
Thank you.
Okay, thank you, Asanka. And are there any more questions from the audience? Yeah, I have one question, sir, from the point where the Asanka asked the question. So if you take that two graphs, so then how we can physically estimate the parameters? Like, so our main objective should be to match the actual requirement with the simulated model, simulated parameters. So how this is physically done?
Yeah, we already governed the actual response of Neonate using flex sensors during its bending behavior. Then we suggest a hypothetical disk model to describe the bending behavior of a Neonate actuator. then we govern a mathematical model to describe the bending behavior of our soft robotics actuator, also Neonate actuator, uh, alongside its real-time bending. After that, we consider a actual response as a benchmark to describe its mathematical lump parameters by overlapping the mathematical response of the systems of our system.
Okay, based on this method, like once you estimate the particular parameters exactly for a particular application, so then after that, as you mentioned, like once you fabricate that material with the relevant pressure and mixing ratios exactly, so then once we using this material anywhere in the world, so are they responding in the same way, or still, I mean, do we need to do optimization later as well?
Yeah, currently we develop this Neonate actuator by mentioning the specific material parameters to represent. For example, if we want to bend our Neonate actuator for 90 degree at 2 bar, then we have to mention we have to design specific mixing ratios. We have to design the actuator behavior. For example, cavity size and length, and some other things. Those are the depend on our design.
Okay. Okay, thank you, Tisera, for your valuable presentation. And so now we can move on to the next presentation. Next presentation is on indoor localization system based on Bluetooth low energy with inertial sensor assist for resource constrained environments. The presenter is Lahiru Gunatilaka and Thamira Hettivatta, are computer science and engineering undergraduate in University of Moratuwa. So over to you, Mr. Lahiru and Thamira.
Our project, Indoor Localization System based on BLE with Inertial Sensor Assist. The keyword inertial sensors refers to accelerometer, gyroscope, and magnetometer, and BLE is used as the shortened form for Bluetooth Low Energy. We are a group of 2 members, Lahiru and Tamira. Our project has been supervised by 2 supervisors, Dr. Chandana Gamage as our internal supervisor and Dr. Subhaj Chas as our external supervisor. Let's have a little introduction on indoor localization. It is impractical to use traditional localization technologies such as GPS for localization in closed areas such as airports, shopping malls, and multi-level parking areas. Indoor tracking requires highly accurate localization compared to outdoor localization, since indoor spaces is limited and densely populated with objects. Trending indoor localization requirement is 1 to 5 meters of accuracy for massive indoor areas. Modern low power consuming chips enable us to build power efficient solutions. Object tracking can be done by attachable sensor tag, and self-localization, which is a requirement of indoor navigation, can be done using smartphones. As we mentioned before, it's impractical to use traditional technologies for indoor localization because GPS signals cannot penetrate through buildings, so error propagation is very high. Device feed tracking technologies such as camera-based localization technologies and Wi-Fi RSSI, received signal strength indicator, and CSI, channel state information, fingerprint-based systems cannot gain better performance on indoor localization because still it is impractical to build an universal model based on these technologies. And also the signal interference caused Wi-Fi CSI fingerprinting to fail. Using existing radio wave based infrastructure such as Wi-Fi and RFID or radio frequency identification is not a power efficient way to localize limited battery powered devices such as attachable tags. Location calculation within the device itself is not an effective solution for a low powered device since they have the drawback of high power consumption. When it comes to deployability, a localization system should be simple enough to be set up easily. Our objectives in this research are implement a BLE RSSI based localization system which can locate a sensor tag or a smartphone with high accuracy. Implement an IMU based motion tracking system which can output location relative to an initial point. researching to overcome common issues of above systems, and then integrate both the systems together to get a highly accurate indoor localization system. The phones we carry nowadays are capable of supporting full-fledged indoor localization, since they contain necessary sensors to measure initial values and communication technologies such as Wi-Fi, Bluetooth, and BLE. Since we carry this much complex device in our hand, we were motivated to design a system that could solve indoor localization problems. Lack of precision indoor localization systems in the research domain motivated us to develop an improved indoor localization methodology. Since there is no robust and industry-leading method for indoor localization, the research domain keeps on expanding, trying different techniques to build a reliable location estimation system. With the growth of modern technology, microcontroller sensors, communication modules become reliable, miniaturized, and energy efficient, enabling us to build low power consuming systems. The importance of people tracking during a pandemic situation also motivated us to carry out this project even in COVID-19 pandemic situation. Now let's focus to the methodology. The proposed system consists of following components. End node. This is the item we need to track and localize, which is the sensor tag or the smartphone. Receiver nodes. They are fixed to the infrastructure of the indoor environment. A BLE receiver and a Wi-Fi module is connected together. BLE receivers collect broadcasting data of the end nodes and send them to the cloud server with Wi-Fi using MQTT protocol. Backhand Server processes the collected RSSI data and IMU data to calculate the position coordinates to be stored in a database, which will then be used to visualize in a web user interface. Let's have a look at the end node.
In here, the inertial sensor data would be broadcasted to receiver node. We worked on existing beaconing technologies such as iBeacon, Eddystone Beacon, and Old Beacon, where we had to find a protocol that allows at least 21 bytes of broadcast payload size. In payload utilization section, inertial sensors read at 10 Hz frequency and the values are calibrated using predetermined parameters. Then, sequence number, end node ID, sensor data are added to the payload and then broadcasted. Then let's move to the receiver node. When sending broadcast data to the server, the broadcasted data packet are captured by BLE receiver, where the BLE receivers keep on scanning for data all the time. Since we need to scan and transmit at the same time, Wi-Fi and BLE should run at same time. So, two ESP32 devices connected with SPI are used. After capturing data, RSSI and Wi-Fi MAC of the BLE receiver node would be added to a data packet and will be converted into a JSON object. Then converted JSON object would be transmitted to a MQTT broker.
These are real photos of the test setup in two different angles. The points A, B, C, and D are marked on the ground. The receiver nodes are marked in red circles. The left side image shows the powered on sensor tag lying on my hand, and the right side image shows a close-up of coupled ESP32 devices fixed on the window.
Then let's move to backend server. This image shows the abstract view of the backend server. The MQTT broker publishes the received message from ESP32 client to the Python server, who is a subscribed client. Each JSON object has a sequence given by the unknown. The Python program forwards the JSON estimation algorithm and the output is fed into the common filter. The bucket waits for at least 3 similar sequence numbers from 3 distinct ESP MAC addresses to feed the respective RSSI value to the trilateration algorithm. The output is then fed into the common filter and final position estimation is stored in a database. After that, web user interface reaches the database to visualize the position of the end node.
Next, we'll discuss about RSSI data processing. First, we must get the coordinates of BLE receivers from the database and send them to the trilateration algorithm with the RSSI values. Then we need to smooth out the RSSI data to avoid sudden surges and spikes using low-pass filters such as moving average filters. Then the RSSI values are converted to distances and undergoes trilateration. Least square array is used to improve accuracy of final estimation. The received JSON objects from MQTT broker are filtered according to sensor ID and sequence number before feeding to the trilateration algorithm. The distance can be obtained by feeding RSSI values to the mentioned equation. The figure shows the trilateration scenario. The trilateration method requires at least 3 known positions of receiver nodes and the reference distance from each receiver node to the end node. The position of the end node can be determined by the intersection point of 3 reference circles drawn by the receiver nodes. The distance d is the diameter of each receiver node marked in blue. The red dot is the end node. When considering the returning area, there will be some residual Ri, which is the difference between di and the estimated distance of ei as shown in the figure. The distance di can be represented as an equation of a circle. We can solve a set of equations by representing them as a matrix to find the coordinates of the end node. Since there are only two variables to be determined by n number of equations, the system is overdetermined. Therefore, the least square error method is used to find the position of the end node, which is the minimum sum of squared residuals.
Now, let's focus on IMU data processing. This can be divided into two main parts. In the first part, we determine the orientation of the device, and in the second part, we determine the acceleration values of the device from the orientation of the device. The earth reference acceleration will be calculated by multiplying the acceleration data of the device reference frame with the rotation matrix. Then smoothen the output acceleration data by moving average filter. For orientation calculation, we had three options: oil angle based orientation calculation, Magritte filter, and Mahoney filter. But we avoided using oil angle based orientation calculation for avoiding the gimbal lock. Mahoney filter and Magritte filter are using quaternions for orientation calculations which are not affected by gimbal lock. From Magritte and Mahoney filters, we had to choose a one filter. So when we are researching about them, we found a very informative research. It was an orientation filter comparison research. From that research, they have concluded that the Magritte filter is with better performance than the Mahoney filter. Therefore, we used Magritte filter for orientation calculation. After calculating the orientation of the device using the Magritte filter, the earth reference accelerations can be calculated by multiplying the acceleration values of the device reference frame by the rotation matrix, the second matrix in this slide. Then we will get accelerations toward south, west, and down. The IMU sensors of our devices should be highly calibrated for avoid drifts due to noise and bias of the sensors. Now let's focus on filter fusion. In filter fusion, in the first stage, we receive the RSSI and IMU based localization data, and then the initial point would be estimated by the RSSI data, and then after that the filtered data by integrating both IMU and RSSI data would be output. We used Kalman filter for filter fusion. This is our Kalman filter. We get the state vector which is consists of position and velocity, and the covariance matrix is in the right. So the prediction is done by using IMU data. Pk is the known equation of motion. The S equals ut plus half at squared and plus some errors. Vk is also same. V equals u plus at. Then we can represent those equation in the following matrix form. Then the matrix equation can be represented as the last equation. Wk is the error matrix. Then the covariance matrix also should be converted as the first equation. Qk is the noise of the speed and position with IMU data. Next, we are moving to the measurement stage. We only can get a position data with the help of RSSI data. We cannot get any speed data from RSSI data. Therefore, we need to convert the state vector onto the same space that the RSSI data are in, only as the position data. The H should be defined by us as suitable. The covariance matrix also should be converted into the same space as in the last equation. Then the final stage, the estimation stage. So we calculate the Kalman gain. Kalman gain is a measurement of how much we should trust RSSI data and how much we should trust IMU data. The estimation position is k times RSSI based data and 1 minus k times predicted data. In here, we can see the experimental setup map used for testing. The blue circles are receiver nodes, and the A, B, C, and D are the points on the ground used for testing. This figure shows the path of the end node moving from A to B to C to A. The dataset was generated in the previously mentioned experimental setup environment. Mean and max errors were calculated for walking and stationary. These are the results based only on trilateration. This trajectory path was created when we test the IMU based location estimation. Path was A to B to C to A. Mean error was 1.54 meters for stationary, 1.77 meters for the walking, and maximum errors are 2.37 meters and 4.14 meters. Here we have the trajectory path based on the Kalman filter based position estimation. Again A to B to C to A. The mean error was 1.544, both stationary and walking, and maximum error was 2.32 meters stationary and 3.5 meters for walking. The experiment was done using an N node which did not have an omnidirectional antenna. With N nodes with omnidirectional antennas, the RSSI-based results and combined results would be more accurate. Another limitation that we faced was that even if the expected data broadcasting rate of the N node was 10 packets per second, but the actual data broadcast rate was 7.6 packets per second. It is very important to calibrate the IMU sensors before the experiment, as the noise and the bias of the IMU sensors can impact the accuracy of orientation and the localization results. The initial position should be calculated according to the RSSI data, as the IMU system outputs the relative position to the initial position. The proposed approach broadcasts IMU data and performs IMU-based localization outside of the N node. Therefore, the accuracy of IMU-based localization in our system cannot overperform the in-device IMU-based localization. Still, this can be useful for indoor localization applications with low power nodes.
This is the demonstration video of the project. As you can see here, we start to move from point A towards point C, then we move from point C towards point B. Finally, we move from point B towards the starting point A. In the right side window, you can see the estimated position of the handheld device as a red dot. The landmarks A, B, C, D are marked in green, and the position of the receiver nodes are marked in blue dots in the GUI. A database was implemented using MySQL to store location data of the end node, receiver nodes, and the information about indoor area. An API was implemented in PHP to fetch data from the database and visualize in a web application implemented in React.
These are the references that we followed for the research. Thank you very much.
Thank you, Lahiru and Tamira, for your nice presentation. And now the floor is open for questions. Do you have any questions from the audience? Lahiru and Tamira, I have one question. So this your algorithm, is it basically for locating the device, or just to track a trajectory, or something, or find a particular whatever within the localization to find something? What is the main application of your algorithm?
The main application is to locate the handheld device. So it could be a mobile phone or sensor tag, which can be attached to some kind of objects, like normally day to day we are using in work stories like Wi. So we can track those devices.
You can track the device. So based on your algorithm, so have you compared the performance of your algorithm with any other existing similar kind of algorithms, their performance?
Yes, we have compared this, but normally most of them was based on RSSI fingerprinting technologies, and also IMU initial sensor based, and also camera based systems also presented, but we couldn't find any commercial based, like practical solution for that means kind of universal model, because we need to deploy it. As an example, when we get a RSSI based solution, fingerprinting based solution, it should be trained for a particular Indo area. But this solution can be used for any area. Only we have to save the locations of that sensor nodes in the Indo area. Bluetooth sensor.
Okay, so with that you are using so this product. Have you thought about like like developing a platform supporting this localization algorithm, and on top of that, developing any commercial applications where you can commercialize it?
Yes, there are so many use cases, like we can track objects in factories, laboratories, and some storage areas, and also there may be applications of likewise in shopping malls. We can give some suggestions for where to go with your preferences. Likewise, while tracking our question. Likewise.
Okay, thank you, Lahiru and Tamir. And any other questions from the audience?
Oh, yes, I have one question. Can I go ahead?
Yeah.
Yeah, so my question is like, so I observed that you have used 3 receiver sensors. So like, can the accuracy be improved by increasing the number of sensors, or
Yeah,
change in the placement of the sensors?
definitely yes. In basically we are using multilateration, but with available resources, we had to go to 3 sensors nodes. That's why we were using 3 sensor nodes.
Right. So potentially, like if we increase the number of sensors, we can increase the accuracy. Is that the case?
Yes.
Okay. Right. Thank you.
Okay, thank you, and thank you, Lahiru and Tamira, for your nice work. So with that, we can move on to the next presentation. Next one will be a poster presentation. The title of the presentation is Towards an Abstract Style for a True Push Communication Enabled Rich Web-Based Applications. The presenter is Nalaka R. Disannayaka. So he's born in Anuradhapura, a sacred city in Sri Lanka, in 1982. He received the BSc degree in Information Technology from Sri Lanka Institute of Information Technology in 2007, and the MPhil degree from University of Colombo School of Computing in 2017. From 2007 to 2017, he was working as a student instructor, assistant lecturer, software designer, and senior lecturer in various institutes. He is currently working as a senior lecturer at the Sri Lanka Institute of Information Technology, Malabe, Sri Lanka. He is the author of over 30 peer-reviewed conference papers and 3 papers. His research interests include software architectures, design patterns, web engineering, and rich internet applications. He contributed to the domain of web engineering by introducing architectural styles, design patterns, and terms and definitions from some concepts. Nalaka, over to you. You can start your presentation.
Hello, I'm Nalaka Sanayaka, and I'm about to present my work titled Towards a Style for Push Communication Enabled Rich Web-Based Applications. Let me start with explaining the background concepts. The targeted type of systems is called rich web-based applications, which is a type of web-based systems. These advanced systems have rich GUIs which communicate with server using an advanced communication model called delta communication. The rich GUIs together with advanced delta communication improve user experience. Most of the web-based systems we use nowadays, like Google Apps and Facebook, are actually rich web-based applications. Rich web-based applications use push communication for server to push content to clients. Push communication helps to further improve user experience by implementing features such as notifications and real-time updates. However, the core technology of web, which is HTTP, is based on request response model. That means it supports pull communication by default. Therefore, it does not support implementing push communication. Still, in rich web-based applications, push communication can be implemented in form of delta communication. There are technologies like polling to simulate push communication based on the request response model. And also there are advanced technologies like WebSocket, which can implement true push communication where the server elements push content to clients without using request response model. These advanced true push communications help to improve performance and scalability, and as a result, the user experience is also improved. The problem in this environment is that integrating push communication into rich web-based application is complex, and there are no abstract architectural styles to realize the integration of true push communication into rich web-based applications. The available architectural solutions like Sphere and Jaga are based on a set of specific technologies or realize only push simulation. Hence, they poorly address performance and scalability, and as a result, they are unable to improve the user experience. The motivation is if there is an abstract style for rich web-based applications to realize the integration of true push communication, it will show the runtime configurations of the elements required to implement true push communication enabled features. To address this complexity, we propose to introduce an architectural style which is capable of realizing the elements required to implement push communication and the configuration among these elements. This knowledge will also help to understand which technologies should be used to develop these elements and how to test them as well. We try to understand the common characteristics and essential features for push communication enabled rich web-based applications and utilize that knowledge to extend the style named Rework style, which we have introduced in the early stages of this research. The Rework style can already realize the standard rich web-based applications, and our extension will help to realize how the push communication can be integrated into rich web-based applications. The resulting abstract style will assist in developing elements to perform true push delta communication using advanced WebSocket technology to improve the performance, scalability of rich web-based applications in the direction of increasing the user experience. This is the basic concept of our ongoing research. Thank you very much for your interest.
Thank you, Nalaka, for your presentation. Now the session is open for questions. Are there any questions from the audience? Nalika, I have one question based on your algorithm. How you can use your algorithm to enhance the applications? What kind of applications it is more suitable?
It's actually not an algorithm, it's an architectural style. It's like an architecture, so it shows what are the elements and how can you implement them. And basically, the core is what we call the Rework style. It can be used for any rich web-based applications, including the client elements with browser-based app or desktop or even mobile app or even IoT-based device. That's possible. So at the moment, we are working on extending it to realize how to integrate the push communication. So it will be able to use for any system using push communication, actually true push communication.
Thank you, Nalika. Are there any other questions to Nalika? Okay, thank you, Nalak. I think you can extend your framework to further to and we would be able to see like it is used in many other applications in future. Yeah. With that, with that we can move on to the next presentation. Next presentation is on towards a framework for online exam proctoring in resource concentrated settings, focusing on preserving academic integrity. The presenter is Dilki Schlesinger. Is a final year undergraduate at the University of Colombo School of Computing, reading for BSc Honours in Computer Science degree. So Dilki, now it is up to you. You can start the presentation.
Hello, shall I play the recording or is it
No,
possible to play the recording?
give me a minute, so I'll play.
Thanks. Greetings everyone, I am Nilki Felsinger, a final year undergraduate at University of Colombo School of Computing, Sri Lanka, presenting my final year research towards a framework for online exam proctoring in resource constrained settings, focusing on preserving academic integrity. My supervisors are Dr. Tilina Halalawa, Mrs. Shani Fonseca, and Dr. Kasun Karnanaik. So education has been changed dramatically with the distinctive rise of e-learning. As we all know, COVID-19 accelerated the online learning process. So institutions have to not only deliver online lectures but also have to conduct online exams in order to smoothly function the academic programs. At the same time, they have to maintain the credibility of the programs as well. So academic misconducts are very common in online exams because it's like one click away where you get access to all the resources that you need. So academic misconducts are of two types in online exams, which happen on the local environment. So you can look at cheat sheets, use mobile phones, and on the computer itself, you can use search the web, copy paste from notes, and use virtual machines. And to mitigate this online, there are commercial proctoring solutions which have employed third-party trained proctors that watch you through the exams. These are often suitable for on-demand exams. And as the ad hoc method, institutions are using video conferencing, which is entirely manual, and when the numbers are high, it is not a very feasible solution. And of course, in developing countries like Sri Lanka, there's infrastructure problems such as high-speed internet connections, and often students do not possess powerful computing devices to experience a smooth online exam procedures. So there are studies that have been proposed to various proctoring solutions, semi-automated and fully automated. In those studies, the development approaches have been machine learning or rule-based techniques. Often they require extensive feature extraction techniques that demands high computational power, hence they are deployed on cloud. So these studies have been ignored the economic constraints such as access to high speed and in computational power. So there's a question as they can be used in low resource settings, often with unstable infrastructures in developing countries. Which leads to the question about how we can provide a novel approach to proctor online exams in an environment with unstable infrastructure and low resources using data obtained from webcam video streams. Talking about the methodology we used, constructive research methodology. to identify a problem and then construct a solution idea and demonstrates its theoretical connections and scope of applicability to computer science. So first of all, to get the comprehensive understanding of the current context, we used a proctored exam which required the students to use their laptop webcam and the smartphone placed at a distance to proctor them use during the exam, and the video records should be submitted to us. And from the feedback survey we did after inquiring about the experience of these proctored exams, 85% of the participants said that they had at least one issue either with their internet connection or the smartphone or the device laptop they own. So with the understanding of this context, we are proposing that our construct should be a suspicious behavior detection model that should run on the candidate device itself and send a visualized video action recognition report to invigilators real time or at the exam submission time. So our suggestions for this ideal model is this should consume as less network data as possible, and to accomplish that we suggest that it should ideally run on the exam candidate device itself and send the detection results to the invigilator real time or at the exam paper submission time, and the detection records to be in graphical format so that invigilators don't have to skim through videos that are hours long. So we are hopeful that we would be able to develop our construct that cater all these suggestions, and we are hopeful that we would be able to demonstrate its applicability practically and as well as theoretically. Thank you.
Okay. Thank you, Ms. Tilki. And you have done a very valuable work for especially the educational institutions. Now the session is open for questions. Are there any questions from the audience? Ms. Tilki, I have one question. So you said that this is your main focus is you're developing this framework for low resource environments, basically.
Yes.
So in that scenario, so how you are recording, how we are detecting like suspicious activities and passing those evidences to the invigilator?
In the previous studies, they have used different image processing techniques on the webcam videos, first to extract features and then combine them all together and use maybe a algorithm like SVM to predict a probability of cheating. So for each of the action type, or let's say the gaze estimation, or there's mobile phones present, things like that, there's let's say if there's about 6 instances, there's 6 techniques to detect one of like each of them, and then they have combined it. So in my approach, what we do is using deep learning, directly recognizing the actions. So there will be only one model that detects about 8 actions of the candidate directly trained from videos. So we are trying to reduce the number of techniques, like the components of the model, into one ideally.
So then the evidences are, so if the system detects a suspicious activity, does it start recording visually that activity, or just it pass only the that particular probability and evidence?
So we are hoping that ideal model should record the whole video and send only the detection records. So if the invigilators need to further investigate about it, they can of course request the video afterwards. Because our participants have said that if they are given a deadline to submit the video, it takes ages to upload it, like to submit it into the VLE.
Okay. Are there any more questions from the audience?
I have one small question. So like,
Yeah.
in this scenario, so will the detection be happening on a client, the client system, or will it be happening on a centralized server or something like that?
It will happen in the client side because
Right. So
it's costly to transmit the video.
right. So in that case, you mentioned about this resource constraints. So like,
Yes.
isn't that kind of an issue? Like different system clients can have different capabilities, and would that affect the accuracy of the detection model?
Yes,
as
that
per
is
se?
the main challenge we are facing to design this to work on a client side. So that will be further investigated. This is in process right now.
Right. Thank you.
Yeah, actually, I also had the same question, and also like you have to think about like if the students do not have a computer, so if they are working only on the smartphone, so then
Yes.
further the resources are restricted.
Yeah.
So I have to think about that as well. Yeah, thank you, Dilke, and
Thank you.
yeah, all the presenters in this session. I think we learned a lot of new work which will be strengthen the future of technology, especially the physical computing. I think so. We need to move forward all these research work, and ultimately it should be one objective is to bring them into the application domain. So we should be able to have all these algorithms implemented in some application or framework or as a commercial product. So hoping that you all work continuously to develop all your work to that level. So I would like to wish all the presenters very best in your future endeavors, and thank you very much for all the participants for your valuable inputs. And with this, we can conclude this session. Thank you very much.
Yeah. Thank you, sir.
Thank you.
Thank you, Professor Yapa, and the authors who joined the session today with us. Now we can move to the next item in the agenda. So next in the line, we have the keynote speech, which is happening in the main session, and I urge everyone to take part in that session. Thank you.